This material was in an earlier version co-developed with my friend and colleague Paolo Castagna. Those are our email addresses. A.O is apache.org, and this presentation, or an initial version of this presentation, was first given at the ApacheCon conference in Europe at the end of last year, when we were very lucky in that location. We actually had people from both styles of graph databases in the same room, and that proved to be a very useful discussion because graph databases are not exactly very common in the world. The fact that there are multiple different kinds and approaches, there are actually two very, very different communities, and it's grown up on both sides, driven by completely different environment and problem solving to address. Yet they're both based around this fundamental idea. So at some level they're the same, and when you get down to the details, they're actually very different. And having those two groups of people actually talk to each other for once, because they tend to go to different conferences, they tend to move in different circles, and they tend to be solving different business problems, generated a lot of overlap, and it was quite an exciting place for that conversation to happen. If you have any questions as I go along, feel free to ask them at the time. Don't wait until the end. It's a small audience, so if there are things you don't understand, please say so. That's my fault. I will want to correct it, because if you don't understand because I've gabbled on something, somebody else is probably finding it difficult to understand as well. So this is about two graph data models. We'll look at a little bit about what graphs are. We'll just to frame the sort of world that these are both coming from. We'll look at the data models that they both have, and then I'll look at how you can combine them together and give some ideas on what is a good idea to take from one to the other, and ways that I think are actually a bad way about thinking about how to combine them, because there are certain trends that people advocate that I think will not actually give very much benefit. So that's really the sort of gist of the outline. So first question to the audience: how many people here have used a graph database at all? That's more than I often get. Is great. There aren't many people in the world, and so we tend to be a bit diverse. Who's used a property graph database? Who's used an RDF database? Even numbers for once. Property graphs are currently, probably more common and things. There are other graph data models. Oracle's a sponsor here. Oracle have a support their own the network graph model. I'm not going to go into that. To some extent, I mean, the graphs, they're all the same, and they're all different. But we could talk about these two just to draw out the contrasts. What I say is actually going to be quite applicable to some of the variations on them. First of all, who am I? Who's talking? I'm a committer. I was a committer on some Apache projects. The one I commit to most is called Apache Jenna. And I work for a company called Top Quadrant, who make information management tools based on RDF. We use that to capture the data, we use that to display, and we're very explicit to the users that they are working with RDF. It's not a technology that's hidden behind the scenes that solves a particular problem. We're talking with information scientists, with data scientists, and they know they are working with RDF. They actually manipulate the data directly, and sometimes they will edit it directly in their systems. So this is RDF in front of you kind of tools. I've been involved in some of the linked data standards for a while. Linked data, if you don't know, is just for this purpose of the talk, a synonym for RDF. It tends to emphasize more on the data combination, the data reuse between organizations, and RDF is kind of a bit more of the technology, but the difference is kind of not particularly important for the purposes of this talk. The particular standards I've been involved with are the query language called Sparkle and the data formats for RDF. As I said, I contribute to Apache Jenna, and I work for Top Quadrant. So graphs. Why graphs? First of all, this slide actually has a subtext, which is we're not talking about graphs with X and Y axes and squiggly lines and colour schemes. We're talking about graphs to capture interesting data structures. So something almost as simple as an org chart that it naively looks like a tree, because you have the manager, you know, have the head of the company at the top and he has his reports and he has the reports underneath that, does not reflect how companies actually work. This was a graphic that I found on the internet somewhere, another one of fair use, because I don't have the copyright for it, that captures a number of different companies. And you can try and say which ones they are. The original slide actually has the names of the companies on them. But it's capturing the idea that there are companies that do organise as a tree. That would reflect how the organisation works. This one down here, I don't know which one it is, has a very different way of doing it, where there's one centre thing and everything captures. So how would you build something that captures that sort of data in such a way that you're not building something that's specifically for this or specifically for that kind of thing? So you want to capture the idea of how an organisation relates to each other. So you're getting data that can be looked very different ways, and you're getting data that probably changes over time and probably changes for all sorts of reasons. Like if you look at one part of a company, a large enterprise, it might organise in a very different way to another part of the company. And if you want to make something that captures that knowledge from your enterprise, how are you going to do it? One possibility is a graph database, because it can capture these kind of networks naturally. It doesn't assume that there's a single, regimented, organised way that can be turned into tables, can be turned into something much more on the structured end of data. So what sort of use? Reference data. Life sciences do a lot of this sort of thing for publishing ontologies, for publishing reference data. And there are a number of forces that drive them to using graph databases, one of which is they keep changing how much they know, which is good because a lot of this is medical. They want to keep adding to that data in ways that wasn't originally planned, but they don't want to invalidate all the old data. It's not like when you publish the next version of SNOMED, which is a list of clinical terms, that because they've added a new area, you have to go and re-engineer the data modelling of some area that actually hasn't changed very much. A graph database is good at having different data organisations in different places in it. They use RDF because it's a standard, because it's neutral. In this particular life sciences area, key reference data comes from charitable institutions, which are huge in life sciences. They essentially drive the structure of the research end of the things, or national institutions, whether it's the National Institute of Health in the US or other national organisations, and they don't want to be specific to a particular vendor. They're looking at producing data that has long-term asset value, and the pharmaceutical companies, the life sciences companies, are taking this data at the beginning of the research pipeline. So, there are lots of money involved at this stage, and neutrality about formats and nobody has any control is very important to make them acceptable. Similarly, vocabularies, by which I mean just list of terms, just something as simple as the catalogue of some organisation, every stock control unit they put on the shelf. Details of that. That's reference data that they can build information systems around. As lists of SKUs, stock control units, they're just huge, because everything on that shelf has a unique number that says what kind of thing it is, for any kind of things. Shareable data. All the info boxes from Wikipedia have been captured and turned into a big database called DBpedia. So those are all knowledge management kind of, the knowledge-based things, but also graphs give you analysis, looking for patterns in the data, looking for things. So one example of that is Cray, based in Bristol, across the water there. They use graph databases for fraud analysis in a large cable provider based in North Bristol. They talked about it publicly, it's Virgin Media, and they're looking for patterns that show fraud is going on in some way. Extracting information in the finance industry, who have very, very large amounts of data, and where even quite small insights into the data can make very big differences to their profitability. So they're very interested in capturing data in all sorts of ways and then deciding how they're going to use it and look for the patterns within it. Social graphs, so that's a more general idea of the org chart, capturing whether it's Facebook or Twitter or social graphs of robots or something like that. It's a kind of world where graph databases can provide the flexibility at some cost. They're not as fast as traditional databases, if nothing else because traditional databases have had 25 years head start and $25 billion worth of R&D investment, but also there's fundamentally less for the computer to get hold of to do things in efficient ways because of the flexibility. So other use cases on the analytics front, social networks, recommendation engines, you're actually using these quite a lot. If you go to Google and you look up a restaurant and it tells you its opening times, there's a good chance that is driven off a graph from schema.org, where web pages are annotated with information about, and it's hidden in the web page, about opening times, and Google just slurp it out. What Google are doing is providing the vocabulary and the terminology so people can put it in web pages so they can go and scrape it to make their engines look better. But anyone can take that information. It is a web of data that they are creating. Another one I quite like is, I've come across this a couple of times, is organisations start experimenting with graph databases in their domain of business. But the one they actually find it very useful is actually running their business. Tracking what's in your data center is surprisingly difficult at scale. And the really good question is, if I walk up to this rack of computers and I rip the power cord out the back, what stops working? Because by the time you've got high-level applications using microservices, using databases moved anywhere else, they're running in virtual machines, which you can move from machine to machine, to actually know, because those are different layers of responsibility and engineering teams about what's going on, it's actually quite difficult to have that picture of which applications, high-level things sitting up here, are using the nasty hardware down at the bottom so that when you turn the hardware off, it has an effect. You may know where you put them originally, but then somebody's optimized where the VMs are running, so they've moved them. They've moved between machines, they've moved between racks, they've moved between data centers. So it's actually quite difficult to know what's going to be impacted. One quite scary one is an organization only had one way of finding out, which was by turning it off and seeing what happened. And they were just being honest about it, so they were very interested in using graphs to capture all the information from those different levels, because different groups could then take out what they needed to do to get it. They could create an asset for running their data. Another one, knowledge graphs, happenings, people, places and events is a very common way in anything driven from history or recording happenings. And the happenings tends to be also in national security issues, modelling things like that, and having well-founded principles about what it means to make an observation. Just because you have seen a ship go by, A, you might be wrong, B, when it happened, what you used, how much of the silhouette you could see, all sorts of stuff relates to what the quality of that observation is. And if you're getting something that's collecting information from lots of different observations, what you've recorded about observing a ship might be different from what you observe about in internet traffic that you've monitored. And the other one that is kind of happening is product catalogues and knowledge graphs across the organisation and be able to react to situations. A large company is working with us to build a catalogue of all their products and what those products are made of, so they can answer the question when a large, in this case American, very large chain of supermarkets phones up and says, there's been a report that such and such a chemical causes cancer. Which of your products are affected? If it's the government phoning up, life's actually quite easy in the sense that governments are quite relaxed. If you can give us the answer in 6 months, they might be quite happy about that. The commercial world wants the answer in like a week to be able to react to the bad publicity that might go through. So those questions come in after you've collected the data, rather than there's some application that can already answer this question. So how do you have data that you can react to situations? And graph database is one approach to explore there, because you can just chuck everything in and then decide how you're going to use it later. There are, it's unfair to say there are two, but the two I'm going to talk about are RDF, Resource Description Framework. We're in a media centre. It is not the company with the same name. There is a large media company called RDF, which gets confusing when you're doing Google searches. That's based around W3C standards, the World Wide Web Consortium. It's grown up, and in fact Bristol has actually been, Bristol University, and people there started a lot of the work about, I was going to say 10 years ago, but I think it's longer than that. I think Simon here knew those people back in the day, worked with them. So it's actually got a strong Bristol connection. It's been very open in the way it's developed. It's always gone through standards, whereas the property graphs model is driven by a different need. It's much more of an industry standard. It isn't planned with committees. It's grown up over time, and different systems implement variations of it, and over time they come to a consensus about what the data model is. And just at the moment, that's coming together quite sharply within one particular project that is becoming the de facto reference sense of what it means to be property graphs. So when I talk about property graphs here, I'm really referring to that particular system, and I'll try and bring out the fact that because it's emergent standards, there are variations that go on within that. The centre that this is happening particularly at the moment is an Apache project called Tinkerbop, and that's somewhere in the Apache incubator at the moment. They are moving very fast, and they're pulling in not of the Apache projects, but also they're being influential into the commercial systems like Neo4j and a number of other ones. And it's an interesting part at the moment because companies are getting bought and sold, there is money flowing, people are interested. So what is a graph? Oh, an RDF graph. Let's go. Sorry, I missed that one. Okay, so I'm going to cover these two data models in order. I have an apology. I'm much more on the RDF side. I know much more about that. I have done some work with property graphs, but I'm more embedded in the RDF world. So apologies if it seems a bit skewed. So what's a graph? And this is true. I mean, a graph is a set of edges and a set of nodes. Mathematical definition, and it's true for the things. I could pick up about what Dave Cliff said, which was interesting to see. He had a whole lecture on graph databases about computer science being separate from mathematics. This is the parts of computer science that we don't like to say it, but it is quite a lot of maths. And it's useful because those algorithms that work on graphs are known to be extremely expensive to execute, so understanding the algorithmic theory, particularly in the property graphs world, is quite important. But a graph is just a set of links. And in RDF, a link is also called a triple because it has three parts. It has the subject, the thing you're talking about. It has the predicate, the relationship with something, and the object, the thing, the arc, the edges pointing to. Edges are directed in these graphs. So you can talk about me. You can say my name is Andy. Me in this case is going to be a URI. So that's a long string that gives me a globally unique identifier for me. And when in the RDF and the linked data world they talk about semantics, that's usually the first thing that we're talking about, is giving well-formed unique names to things, so that when I say my name, Andy, me, this thing here has a name Andy, you know that it's not because there's somebody else called Andy. Bumped into a friend of mine who's got the same name, the same given name as me here, so you know which one you're talking about. And if you want to make some other assertion, like the talk was given at a particular time by a certain person, you can use my URI there, and you know you are talking about me, not another talk, and it won't be confused with that if it ever encounters something in the data. The predicate is the relationship between the two things. That in RDF is always one of these globally unique names, so that when you say a name of something, it's the name of a person. It's not a name of something else. You can be that specific or you can be general. When you start combining data, that's important that things don't accidentally end up referring to the same thing when they didn't mean to, because at that point you will have messed up your data in such a way you will have to start again. You can do a lot of damage to your data. So one of the things that RDF stresses is do no harm when you combine data. It makes sure things are kept apart until you decide that things are the same. Two things can have the same name. No big deal in RDF. It keeps them apart until you say otherwise. So the things that can go, particularly in the object slot, are these long universal names, usual sets of strings, numbers, dates, those sorts of things. And there are some mysterious things called blank nodes, which are where standards groups spend most of their time arguing about and actually aren't always that important. And they cause more trouble than possibly they were ever worth, a lot of which is my fault. If you get bored in these committees and some of them on the phone, it's a bit boring, I have a standard stock set of questions that I know will give me a chance to wander off and get coffee or something like that while they discuss them amongst the theorists. So just keep a filing cabinet of interesting questions. And there's only really one question you ask: what about blank nodes? It's not a good idea. Anyway, this is an RDF graph. So it's got somebody who's... So all those prefix stuff is away because those long names are long. We don't like writing them. So a prefix is the bit before is added to the bit after to produce the long name. So Alice here is actually http://example/mydata/Alice. So that's the name of that node in the graph. FOF is a vocabulary developed originally by people in Bristol, by Libby Miller and Dan Brickley. It's friend of a friend. It's about talking about people and what their names are and what their Skype IDs are and email addresses and things like that, but also who you know. So Alice knows Bob. To your eyes, and this is the sort of thing. So that relationship there is defined to say it goes between actors in the system. Alice is of type person, RDF colon type, because RDF is one of those prefixes. Long name, it's one of the core ones inside the standard, so that's why it's www.w3.org, blah, 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 RDF syntax. So that says Alice has type person. Alice is a person. Good, useful thing to know. And she has a name, Alice Smith. So I've said something about Alice. And that, there, is the stuff written out in RDF. And yeah, looks like a record. It's a record with fields that you can have any field you like adding on to it. You're not prescribed to some schema unless you choose to be. You can just add stuff and say things, whatever you want about those things there. Another little bit. This is about Bob. So somewhere else on the internet, it's bound to be right. So Bob is both names, Bob Brown, and he's a type person. So that's what that one's saying. That's lost that first name. Sorry about that. And in RDF, you can combine the data. You just put the two things together. You just concatenate the files, and that will be the graph. I've now combined that data, and I've talked about those people and what they and their names. Data is not much use unless you can get it out again. So this is a query language for RDF, standard one, called Sparkle. Same sort of prefixing stuff. Somebody who's actually at this conference described it must be SQL-like because it begins with the word select. So select, these are variables, that's a pattern. Find me, for Alice, who does she know and what names do they have? Because names are more useful to show to people than URIs. And you can write increasingly complicated queries because it's a relational algebra-based query language, so you can nest things, group things, and do all the things that you might expect of something of that class of languages. And you can update it. So, slight plug. This is Apache Jenna, top-level project at Apache. So there are about 200-odd top-level projects. I really put this one in because despite this talk being branded as being the big data track, I just wanted to say in Apache there are a lot of other things other than big data projects. Big data is very active, very important within the foundation. I just would like to say there are actually quite a lot of those. Tomcat, for instance, is an Apache project. And some of the other projects feel sometimes they get a bit forgotten, basically. And there are a number of RDF-related projects. NE23 for converting any kind of data into triples. Marmotta is another RDF system, as is Clarezza. RIA here, well, that is actually a big data system. That is an RDF database built on top of a Cumulo with very strong emphasis on security, which comes from running on top of a Cumulo. So, yeah, may be used in certain institutions we're not allowed to talk about. The property graph model is not defined by a particular document. You can't go and look up the definition of property graph, really. It's become emergent. There are certain systems that are more influential in driving that and effectively define the model. So to some extent you have to then go and look at what they do and then extract it out. There are a couple of papers that have written these up in applied technology journals. A property graph is a lower level concept. So again, it's a set of nodes and a set of arcs. They call them vertexes and edges. Like all good math graph things, there are different names for the same things. But the difference is fundamentally each thing in the system gets a unique number. And it's given that number, and then you can add things like properties with attributes, which are short names and values. So each vertex or even each edge in property graph models, one of the big differences, can actually have some characteristics applied to it. And you end up with a directed multigraph. And even a single link can be a lot more complicated. So in a property graph database compared with an RDF database, you have less links because in RDF everything is a link. When you say to a name of a person, to their email address, that's going to be a link. The property graph splits the values and characteristics of things away from the relationships between key concepts in the system. And then you can even characterize the relationships within the model, whereas RDF you have to do it by modeling. So we've got something that's the same.
That's a good question.
Yeah.
I'm not that familiar with RDF, to be honest, so it might be a stupid question, but we'll see. So in saying then, potentially in RDF, if you have some sort of relationship between two things, that they exchange something, you can model that as an edge. But if they exchange the same thing multiple times, how do you...
So this comes to
that they're different?
That is not a stupid question.
Right.
I think you've actually come to one of the fundamental driving differences between the two systems. In fact, in two ways. First of all, if you look at RDF as a knowledge management system, RDF is like a seminar. It's really low level. To use it, you build structures on top of it. And one of the structures you can build enables you to capture what you do. So as you wouldn't put on a link, this happened at such and such time, you'd say, actually, there's something important there. There was an event occurred. So you turn it into a node in the graph and say, Alice sent an email message and point to an event, and the event would go to Bob. And you extract that out as part of your data model if it's important to you. And in fact, if you look at the graph databases booked by the Neo4j people, that is one of the examples in the don't do it this way section of the anti-patterns at the back. Because if that ends up with lots and lots of characteristics, it's actually quite difficult to deal with. So you approach the same problem, but you use different techniques to get to it. You've also stolen some of my slides later on, don't worry. But that shows the different approaches coming into doing it. Access, Tinkerbot Gremlin is a domain-specific language you can embed. I think that looks a bit like Groovy. You can do it in Java. Tinkerbot itself is a reference implementation. Reference in a sort of informal sense is for any JVM, so there's Clojure ones and stuff. It is driven out of the Java ecosystem at the moment, but the general idea is applied in other ones. It's a kind of leading example. And there's a higher level, more, I wouldn't say more traditional query language, but a query language that you write down and execute as a script rather than write a program to do it, called Sipho, now being turned into, which comes up from Neo4j, for Neo Technology. They are in the process of turning that into a more open system. They're going to still develop the language, but the development process is moving into the open. It's sitting on GitHub somewhere, and they're moving slowly in that way. That's an example. It says, do some matching, which will find you some data, and then for each of the things that you've in this list, take what you found, you is going to be a kind of person, get the friend relationship to them. So it's on the same sort of idea that people, particularly people who are not programmers, not all data scientists are programmers, which is sometimes comes a bit of a shock, want to work in languages that are more declarative because they're closer to the way they think about their data. Writing something like these Gremlin scripts is great for programmers, but it's not even necessarily the way people think about things. Connection, whereas in RDF everything is at least logically over HTTP, the property class world is much more defined by API because there's less emphasis on data combination and more on capturing semi-structured data going together. And that is also reflected by the way how you would combine data in the two systems. There's some Apache stuff. ASF is the Apache Software Foundation. Tinkerbot, that's just coming in. They're technically in the process of becoming a top-level project, which happen fairly soon. Apache Spark has a graph engine on top of it. Apache Giraffe, which is the implementation of Google's box synchronous protocol. Apache Flink, another system, has a specialization in something called Jelly. So there are lots of systems around and happening, and these are big projects. I mean, Apache Spark is simply enormous. So it's another place where things are happening. So trying to capture the relationship between the two. The anecdotal difference is, if there's an argument about what some data means, in the RDF world, you dive for the specs and you find out where the text is and you say, no, it says that, or it says that, and then you argue it that way. In the property graph world, you go and look at the code and say, well, this system does that. And then you say, well, that system does that, which one's right? And then you have a discussion about it. So those are driven by very different development processes that have happened for these things. RDF is about information modelling and information exchange, where the property graphs is much more about analytics, about using the data within a given collection and less about linking it together. So, for example, all your vertices have unique numbers in property graphs. That means to combine them, you have to make sure that those numbers are not going to clash. Surprisingly enough, numbers tend to start at 1. So they go 1, 2, 3, 4, 5, and this data also goes 1, 2, 3, 4, 5. You can't just put them together without doing a little bit of work to keep them apart, because there's no reason why actually reading the same data will actually give you the same numbers, because it could have done it in a slightly different order. It doesn't matter in the property graphs world, that's just how it works. One of the things that people talk about is layering one model on top of the other. We put property graphs and then use an RDF engine, or an RDF graphs on top of property graphs as an engine. But I want to ask why you would want to do that. If the idea is because you exploit the really good capabilities of the underlying system, that means you're going to be able to see the underlying system. So now the person working with the data not only has to work with, say, the RDF model, they also have to know what the implications are of the underlying property graphs model. So now their world has got 2 of them in. That doesn't make it easy for people to work with. You may end up with the best of the best. You also get the worst of the worst. And it becomes a system where it's quite fragile. You can't go and manipulate your data in the underlying technology system, because the way the other one was built on top of it needs to remain consistent. If you do it in a different style underneath, you are almost certainly going to break your data. Broken data is quite bad, because it's not a case of, oh, my data's broken like a program, you just rerun it. You can break your data in silent ways, in which you will not discover for several months, and then you can't remember what change was made. Data is long-term, sticky and persistent. If you break it, if you damage in it, you are in a very dangerous position, because it's not like a program that you can rerun. It's something that is pernicious and insidious and has probably driven processes off it, and you are going to have to start again from scratch at some level. So it's not that easy to use one of those sets of tools on top of the others, because the reasons you'd want to do it also make it much more complicated for people. But I would say there are things to take from either system. For RDF, if you're going to combine data, use names that when you put data together, don't conflate things. So you don't accidentally have everything about node 1 over here, which is me, and everything about node 1 over here, which is one of my pet rats, and combine the system and then find out mine, you know, I've got 4 legs, or something like that. That's what RDF has come out of, that tradition, and it's useful. So put URIs as real data type objects, which are different from strings, into a combined model, because that's a useful feature. The entire emphasis on data formats for exchange. RDF is very strong on formal syntaxes that you can write out in one system, read into another, have never met before, and you will read the same data down to exactly what the syntax on the in the file is, and the squiggly bits, and how to deal with international characters, and all that sort of stuff. The property graphs world doesn't tend to emphasize data exchange. It doesn't happen very much. So their formats are written on top of XML or JSON or something like that. They tend to encode the details like the numbers, because they're more like dump formats, so that if you were to restore off that data, you will get the same thing as you put in. But giving it to someone else isn't, you can't just take a database dump and restore it into a completely different database and be absolutely sure it's going to do the same thing and you've actually exchanged data. So there's some emphasis on that, and the query stuff is all based on relational algebra. There was nothing novel about doing it. I think it was a complete reuse or rip-off or synergy. Isn't there a difference between academia and industry? In academia, it's plagiarism, in industry, it's synergy to reuse stuff. And URIs do matter. I found this on Twitter. I don't know if you can see this very well. That is a large monitor lizard of some kind, a goanna, and it was heading towards a Newcastle pub. Now, there's a few things to know here. First of all, the good news is this is Newcastle in Australia, So if you had URI for that place, we'd at least be able to, if the machine were ever looking at this, we'd know that it's not talking about Newcastle upon Tyne or something like that, one of the ones in America, which would be good news if you happen to be in the area. There was some comments like, that would be a really bad day to be on door duty at that pub if that turned up. The other good thing about it is it's not actually known to attack people. Because that particular variety, particular species, doesn't tend to go around and attack people. It's not like Komodo dragons, which are bigger and a bit more aggressive. So URIs matter. We could find this on Twitter. So what are we talking about here? Well, I had to go and look up the name to find out what it is. To know it was about Newcastle in a particular place would be useful. But if you were just capturing information in the UK, you'd probably be a bit more slapdash and just say, it's Newcastle. Things to take from property graphs. The way links and values are separated is much easier for people to use. It happens in the RDF world in a system called OWL, which is one of the layers on top of it, which you end up with two kinds of links. Links that are between concepts in your data model and links which are to values, to attributes, things. And that works very well. It's very natural for people, and it's something that property graph one resonates with people a lot better. And short names for those, because they're local characteristics of the thing you're talking about at that point. And it's much stronger on graph algorithms. That's been where a lot of the applied applications are, so there's actually some quite sophisticated stuff to do that at scale, across machines, in parallel, that doesn't really exist in quite the same way in the RDF world. So, a few conclusions. Graphs are still new to a lot of people. RDF emphasises data modelling and is very strong on things like that. For exchange, property graphs emphasise capture of data and algorithms, and they can be used together to produce something better. Layering, I think, will just lead to everybody being upset because it's difficult to use, it's clunky, and people don't pay much attention to those parts of the system to do it. There's lots of exploration about doing it, and you can find papers that prove it's possible, but what they prove is that it's functionally possible. It doesn't tell you it's going to run fast or it's going to be easy to use. There's practical problems. So they could share technology, storage, data access, query system technology, and now optimizers, which are things that take a long time to develop. The two communities can share those, if just share knowledge, let alone share code. So thank you very much. I've taken longer than I said I would, but thank you very much, and I will take any questions.